Okay, folks, here we are. We're going to talk about the equations section of the AP exam for just a few minutes. On another video, I'm going to work through some past equations from the AP exam just to give you an example of what I'm talking about here. Now, the equations section consists of 3 questions or equations. There are 5 points apiece for a total of 15 points. The national average on this tends to be fairly low. So being successful in this question, or on this question, gives you a leg up on your competition globally. If you do well in this section, your weighted score will be somewhat magnified. Now remember, these all need to be balanced, and they need to be in their net ionic form. All reactions occur. There are no reactions. And the usual grading is as follows. If your reactants are correct, that's 1 point. If your products are correct, that's usually 2 points. And then if you balance the equation, both the mass and the charge, that's another point. So here's 4 points for writing the correct equation. Then there's a question related to that reaction, which is worth an additional point. So of course, if you sum these, you get to the 5 points per question. Now a decent score on this would be 3 to 4 points per question. Now here are some of the common reactions, and I've sort of put them in order I think in which you will see them most often. So you're going to see double replacement reactions a lot. Now for this, you need to make sure that you know your strong acids and strong bases. Remember, those dissociate when aqueous, or when dissolved in water. Sorry. You need to know your solubility rules. Now next year, on the 2013 exam, that won't be as important, but in this year, 2012, it is. Know your polyatomic ions. So take a few minutes at least before the exam to review those maybe one more time. Another type of reaction you're going to see are single replacement reactions, and these of course are a type of redox reaction. These two, I think, are the simplest, and fortunately they're the ones that we see most often. You'll also see synthesis reactions. You might see an element and an element forming a compound. You might see a non-metal oxide reacting with water to form an acid. Remember, when you see this, there's no oxidation number change here. So the non-metal oxide oxidation number for the non-metal will be the same on the reactant side as it is on the product side. And then you'll also see metal oxides in water, and those of course will form metal hydroxides. Now remember, if you form a strong acid or strong base as one of these two products, make sure you dissociate them. If you form a weak acid or weak base, keep them stuck together ionically. Okay, another type of reaction you're going to see are decomposition reactions. So you might see a compound decomposing into its elements. Once again, a type of redox reaction. You could see metal chlorates. Remember, metal chlorates will always produce metal chlorides and oxygen gas. And metal carbonates will form metal oxides and CO2. And a question they like to ask about these two is they say, what simple test could you perform in the laboratory to identify the gas that's produced? And I always like to use the wood splint test. If you take a piece of a wood splint, and you light it on fire and tap out the flame, and you place it into a test tube where oxygen has been generated, that wood splint will reignite. If you put it in a test tube where carbon dioxide has been generated, that wood splint that was glowing will be suffocated. Another gas you might produce in another reaction is hydrogen gas. Of course, if you put a lit wooden splint inside hydrogen gas, you'll hear a pop or a barking noise. Okay, combustion reactions are once in a while placed on the equations section. These are usually simple hydrocarbons. So maybe go through your first 10 alkanes, know your alkenes and alkynes. And every once in a while you'll see an alcohol. If you know your alkanes, you should be able to figure out the formula for the alcohol. Every once in a while you're going to see a coordination chemistry problem. These involve a transition metal ion with a Lewis base. Now the Lewis base used is often ammonia, hydroxide, or chloride. Now a simple way to do these is simply to double the oxidation number of the metal ion, and that's the number of these Lewis bases that will attach to it. We call them ligands. You might not have had a lot of time to go over that in your high school chemistry class, but coordination chemistry, every once in a while you will see one of those on the exam. They're pretty easy. I'll show you a couple on the next video when we work through a couple of the past exams. Redox Locks, I like to call them. They love to use permanganate in acidic solutions. Remember, permanganate here will go from, the manganese will go from a 7+ oxidation state to a 2+ oxidation state. And they like dichromate in acidic solutions, and that will form the chromium 3+ ion. The chromium on this side is 6+. So oftentimes in the question section, they'll say, what oxidation number does the reactant have, and how does it change when it becomes a product? So make sure you can find oxidation numbers. Now, by the way, when you do these redox locks and you're reducing something like permanganate to Mn2+ or dichromate to Cr3+, make sure something else in the equation ends up being oxidized. They love to put sulfite, turning into sulfate, or maybe I negative or Cl negative turning into I2 or Cl2. Now, there are others. You might see a Lewis acid base reaction where you have ammonia coming together with BF3. And what you end up having is a bond forming between the ammonia and the BF3. You rarely will see that type of question, but I've seen it a few times. So let's go through just a couple of these really quickly, and we'll see how you do. Let's say you see a question that says propanol is burned in air. Okay? Well, first of all, we need to make sure we write our reactants properly. Propanol, let's see, it goes meth, eth, prop, and then bute. So meth, eth, prop. Prop has 3 carbons in it. So maybe I would put I draw a quick Lewis structure and say, okay, I know it's an alcohol, so I know there's a OH group at the end, and then these dashed lines will say our hydrogens. So the formula for propanol is C3H 1, 2, 3, 4, 5, 6, 7 OH. Now it's burned in air, so of course it's the oxygen in air that will be doing the combustion. And my products are always going to be carbon dioxide and water. Okay, not too bad. Now to balance this, make sure you do that. Put a 3 in front of the CO2. Looks like we have a total of 8 hydrogens, so a 4 in front of the water. That gives us 6 plus 4. Let's see, that's 10 oxygens. I have 1 there already, so I need, let's see, 9 more. So let's see, would that be 9 halves? Let's see if I did that right. That would be 9, 10, 6 plus 4 is 10. If you don't like to use fractions, you can go 2, 9, 6, and 8. That's just fine. So remember, you get 1 point for your reactants, 1 point usually for each product, 1 point for balancing it correctly, and then they'll ask a question related to this. This question might be, how could we test the gas? Well, this one might be tough because it's a combustion reaction, but they could ask you about the oxidation number of the carbon on the reactant side compared to the product side. So be prepared for that. All right, let's take a look at another one. What if they said, well, let's come up with a good one. Sorry, should have had a few of these at my fingertips ready for you guys to go. Let's say sulfur trioxide is added to water. Okay, sulfur trioxide, pretty straightforward. SO3 is added to water. H2O. There you go, you've got yourself a point. And now what are we going to end up with? Well, these are always going to form oxyacids. Now I always tell my students, hey, for SO3 or SO compounds, you know of 2 oxyacids that can form. You could form either H2SO3, which is a weak acid, so I'd leave it together, or H2SO4, which you could write as H plus and maybe 2 H pluses, and SO4 2 negative. You could also write it as H plus and HSO4 1 negative. Now, which one of these are correct? Remember, the oxidation number has to stay the same. So the oxidation number of sulfur on this side is 6 plus. Remember, each oxygen is 2 negative. On the other side, let's see, the oxidation number of this sulfur, we have 6 negatives, 2, would be 4 plus. So I know it's not that. Now let's see, for the sulfate, we have, yeah, it would be 6 plus. So I would form sulfuric acid in this reaction. So let's go through and try to balance this quickly. 1 sulfur, 1 sulfur, a total of 4 oxygens, and 2 hydrogens. Perfect. So we get 1 point for our reactants, 1 point for each of our products, so a total of 2, 1 point for balancing the reaction. And once again, a good question might be, what is the oxidation number of sulfur both before and after the reaction? Okay, let's try this one. Let's say we take a bar of zinc metal. So zinc metal. And they'll usually say a bar of zinc metal or something like that. And it's immersed in a copper 2 sulfate solution. I'm just going to abbreviate this here. So we have a bar of zinc, and it's immersed in a solution of copper 2 sulfate. So of course zinc, elemental zinc, is Zn. Copper 2 sulfate. Now that's soluble, and it's a solution of copper 2 sulfate, so I need to make sure I show that as dissociated in water. So that's copper 2 pluses and SO4 2 negatives. I know that's copper 2 plus because it tells me copper 2. Now, these are cute little single replacement reaction. The metal will replace the metal ion. So now we have copper all by itself, and the zinc ion will form and associate itself with sulfate, perhaps. So zinc 2 plus and SO4 2 negative. Now that's balanced as it's written. Both my charge, 2 positive and 2 negative, equals 0 on this side. 2 positive and 2 negative is 0 on this side. And the mass, 1 copper, 1 zinc, 1 and 1 sulfate. Of course, my spectator ions are the sulfates, and so I get rid of those. A good question might be, what is the spectator ion? Another question might be, what would you see as this reaction occurred? Well, you would see copper forming on the zinc. This bar of zinc might get smaller, and perhaps a blue solution would turn to colorless. Remember, copper ions in solution are blue. Copper 2 plus, I should say, are blue. So the blue color would begin to fade as the copper ions come out of solution and form elemental copper. Okay, let's do one more, and then if you want to watch another video, I'll go ahead and I'll do a couple of exams for you. All right, number 4 that I'll do for you. Let's do excess potassium hydroxide. So potassium hydroxide solution is added to a solution of aluminum nitrate. Okay, so potassium hydroxide solution is added to a solution of aluminum nitrate. So potassium hydroxide is a strong base. I want to make sure I dissociate that into K plus and OH minuses. And aluminum nitrate is a solution. All nitrates are soluble, so Al3 plus and NO3 negatives. So we notice that this is a double replacement reaction. It's a nice little precipitation reaction. So K and NO3 that will remain soluble. They are spectator ions. And aluminium and hydroxide, remember all hydroxides are insoluble except for group 1, calcium, barium, strontium, and ammonium. So we would form here AlOH3, and that would be a precipitate. Now we're going to cancel out our spectators, the nitrates and the potassiums, and then we'll balance this. Obviously I need 3 hydroxides to associate with that 1 aluminum 3 plus. Charge is balanced, mass is balanced. Now, one more word of advice. Try not to take more than 10 minutes on this section. You need to leave yourself time to answer questions both 5 and 6 that come at the very end of the exam. So if you're spending more than 10 minutes here, try to move yourself along. You can always come back if you finish the exam, but these should go pretty quickly for you. In fact, to make this entire video, I did 4 questions for you along with a brief explanation. It took us about 14 minutes. So don't spend more than 10 on this section. All right, good luck. I'm hoping for you. Bye-bye.